Okay, so now I'm going to start going through notes on chapter 2 of Elementary Categories, Elementary Toposes by Colin McCarthy. So we're going to start by talking about categorical products. So a categorical product of objects A and B consists of an object which we will call A times B, and these two arrows, P1 and P2, which we'll refer to as projections. Now, these have to have the property that for any kind of product candidate, as in for any object T with an arrow H to A and an arrow K to B, there has to exist this unique arrow U from T to A times B that makes this diagram commute. What I mean by that is there exists just one arrow which makes this diagram commute. There may be many arrows from T to A times B, but there's just one that makes this diagram commute. Now, when I say the diagram commutes, what I mean is that if we follow any two paths from a particular object to another object, for example, this path, or this path, and we compose all the arrows along those paths, we get the same result in each case. Okay, so I denote the paths around a particular region commute sometimes by using these green loops. And sometimes we denote this unique intermediary arrow as H, K. Now, there may not be a categorical product for a pair of objects, and there may be many, but it turns out that any two of them, any two kind of categorical products for a particular pair of objects have a sort of unique isomorphism, which basically corresponds to one of these intermediary arrows like U. And that kind of justifies us using this notation A times B. Now, there is some results about this. So in Colin McCarthy's book, the first part of the book is talking about sort of basic category theory, but it does so without using functors and natural transformations and all this kind of high-level language. And so they state these results by the following two theorems. Theorem 2.1, if P, P1, P2 is a product for A and B, and there's an isomorphism from Q to P, then Q, P1 after F, P2 after F is a product for A and B. So that basically says if you have a product and then you have something else with isomorphic objects and projections that are just sort of wound on by doing the isomorphism, then that result will be a product. And then we also have theorem 2.2, which is that if P, P1, P2 is a product for A and B, and Q, Q1, Q2 is another, then there's going to be a unique isomorphism U, with P1 after U equals Q1 and P2 after U equals Q2. Okay? Again, I'm saying there's a unique isomorphism such that that's the case. There might be more than one isomorphism, but that's the only one which kind of goes with these projections in a nice way. So that's all very nice, but I mean, basically what theorem 2.1 and 2.2 are saying is that categorical products are sort of determined up to isomorphism. I mean, there's a bit more content there, but that's the basic gist of it. And that's why we can often sort of write A times B. We can sort of think that we've picked out one of these categorical product objects and we're deciding to use that one. Now, I was deliberating whether to prove those results, but the thing is that as you go through the book, there's lots of other things, like other kinds of limits, like pullbacks and equalizers, and there's also co-limits, and there's also other things, other kind of universal stuff like exponential objects and later sub-object classifiers. And each time you come across one of these, you've sort of got to prove analogues of those two theorems, and it gets kind of tedious. So what I decided instead in these notes is to go to a very high level and prove the general results. But this does involve sort of talking about limits in general and also talking about universal morphisms. So, this is not really essential. You can always just prove each of these sort of things we come up with have the sort of aforementioned properties at a kind of lower level. But, if we sort of hang on through the abstraction, it's probably worthwhile because we kind of get an appreciation for the general reasons for these kind of results. So here goes. I'm going to start generalizing now. So a product A times B with an object A times B and projections P1, P2, and its product of A and B is actually an example of something called a limit from delta L. It's a limit pi from delta L to F. Now, this is what's called a cone. L is called the apex of a cone. So what's going on here? Well, what we have this index category I, which is a category with two objects, which we'll call Y and Z, and only identity arrows. Now, we have a functor F, which is a functor from I to C, and it sends Y to A and Z to B, let's say. So it picks out these objects A and B. Now, I'll say what delta is in a minute. Yeah, I'll say what delta is in a minute. It's a kind of functor. I've told you what F is. L here is the actual product, in this case, A times B. And pi here is a natural transformation from this, what I'll call the L value constant functor, delta L, to F. Pi is a natural transformation from delta L to F. And in this case, its components, pi, actually I should call them pi x and pi y, are P1 and P2. Now, what about this stuff? So the category we're working in, let's call it C, and this index category I is just the sort of thing we need to set up our limit to. It's the kind of shape that when we do this functor F from I to C, that's really picking out a certain kind of part of the category C that we're taking a limit of. And so the shape of I is the sort of shape of the diagram, or the base of our cone, if you like, the place that we're taking a limit of. Okay, this will all make more sense if you watch my video on limits and my video on universal properties, but I'm just trying to sort of go through it quickly. So let's define what this delta is now, this functor. So for an object M of our category C that we're actually working with, that's the category which contains objects A and B and A times B and all of the stuff we're basically working with. Well, for an object M in C, that's what I'm using this notation to denote, we have that delta M is going to be a functor from I to C, and its defined so that for every object in our index category I, delta M sends that object to M, and it sends every arrow in the index category I to the identity arrow of M. Now, a cone of this functor f, which also goes from I to C, is just a natural transformation phi from delta t to f, where f is the sort of functor which we're taking a limit of. And in this case up here, it's just a functor from these two isolated objects to these objects A and B that we're interested in doing a product of. But we're talking in more generality here. So we let c to the power of I denote the functor category, which has objects as functors from I to C and arrows as natural transformations between them. So now we're building up more general terminology because we really want to express limits as universal morphisms or terminal morphisms. So for that, we're going to need something a bit higher level, which is called this diagonal functor, or delta blank. So delta blank is a functor from C to this functor category, C to the power of I. And it's defined so that it sends an object M of C to delta M, and it sends an arrow F from M to N in C to this natural transformation delta little f from delta M to delta N. And that's a natural transformation. Delta f is a natural transformation that has each of its components equal to f. So for every object of our index category, I, the ith component of delta f, is just f. Okay, so the way you can think of this is it's kind of just an arrow between apexes of cones, okay? Cones of arrows raining down on this conglomeration of stuff in the kind of diagram, which is described by this functor f. Anyway, a limit, which consists of an object L of C and a natural transformation pi from delta L to f, is a terminal morphism from delta blank to f. And so here's an example. So the idea basically is that we have this object L in C, and delta L is this functor which is in C to the power of I, and it has this arrow pi from it to f, and it's such that for any sort of cone, delta M with its arrow phi to f, there exists a unique h such that delta h is this arrow which makes this triangle commute, okay? But we can describe this more succinctly. We can describe what a terminal morphism is more easily if we go a bit higher and talk about comma categories. So in general, when we have categories D, E, and F, and we have a functor U from D to E and a functor R from F to E, the comma category, U downwards arrow R, has objects as triples. So an object is in a comma category is an object of D and an arrow. Well, it's an object of D, and the last member of the triple is an object F of F. And also we have an arrow from U of D to R of F. Okay, now they're the objects in the comma category. The arrows in the comma category are pairs of an arrow little f from D to D dash in category D, and an arrow G from F tilde to F dash tilde in category F, which is such that this diagram commutes, okay? So we have R of G after E is E dash after U of F. Okay. So we want to use a certain kind of comma category to describe these terminal morphisms. So let's suppose that X is an object of this kind of central category E here. Now we're going to abuse terminology slightly, and we're also going to use X to denote a functor. Actually, it's not such an abuse if you think about these things as described as arrows from terminal objects, but I won't say too much about that. But let's let F be this category which just has one object and the identity arrow. Now we'll also use X to denote this functor, which goes from F to E, and it just sends this object, this single object in F, this star, it sends that to object X in E, and of course it has to send the identity of that to the identity of X in E. Okay, so now for a functor U from D to E, a terminal morphism from U to X is simply a terminal object of this comma category, U downwards arrow X. So let's see what that means. What it basically means is that a terminal morphism from U to X consists of an object D star in D and an arrow E star from U of D star to X, which is such that for anything similar, as in for any object D of category D, which is such that there's an arrow E from U of D to X, there exists a unique F from D to D star, which makes this kind of diagram commute. So we have that this E can be emulated because you can write it as E star after U of F. Now, since we've reached this high level, we can prove a sort of much more general analog of theorem 2.1, and it's as follows. Suppose we do have this sort of terminal object of U downwards arrow X, this terminal morphism from U to X, and that has object D star and arrow E star. Now, let's suppose that there's an isomorphism I from D star to D hash. Well, in that case, it turns out that D hash with this arrow E hash, which is just E star after U of I minus 1, is going to be a terminal morphism from U to X. So we've found another one just by sort of using an isomorphism on the sort of main object involved, going from D star to D hash, okay? Now, why is this the case? Well, suppose we're given another object to compare with. So, I mean, in the comma category. So we have this arrow E from U of D to X. Well, then E is going to be equal to E of hash UIF, because that's equal to E star UF, as we see here. We're using the functor composition law, but we get there. So that means that IF is this kind of intermediary arrow we need, in the sense that if we do U on it, then we get something that can complete the appropriate triangle, make it commute and so But is it unique? Well, it is actually, because if we assume that there's any theta from D to D hash, which makes this triangle commute, then we get that E is equal to E hash U of theta equals E star U of I minus 1 U of theta equals E star U of I minus 1 theta. And then we know that this thing inside the brackets here is the unique arrow that makes this commute. So we must have that I to the minus 1 of theta is F, because we know from this picture that putting an F in there works. And so that means I to the minus 1 of theta equals F. Rearranging, we get theta equals IF. So that shows that the argument up here shows that using IF does make stuff commute, and the argument here shows that only IF makes things commute, okay? So it's unique. So we do have, given this isomorphism between the D's, we've shown that we're really able to change one terminal morphism into other using an isomorphism I in this unique way. The second result that we need is basically an analog of theorem 2.2, and what it basically says is that if we have two terminal morphisms for the same setup, then they're isomorphic in a special way, which kind of works for the arrows. So let's prove that. So suppose that D1 star with E1 star is terminal morphism from U to X, and so is D2 star with arrow E2 star. Well, that means they're both terminal objects of U downwards arrow X. By the way, these talk of terminal morphisms generally, these talk of comma categories generally, we have to worry about not only the arrows from the sort of stuff going on the left, but also from the stuff going on the right. So, for example, the morphisms between objects in a comma category are usually described by two arrows, one working in the left-hand category and one in the right. But since the stuff going on in the right category is all determined by this functor x, which is like a constant value functor, we only have to work with stuff changing in the U, and we can just sort of make the other stuff redundant. Anyway, suppose we have these two terminal morphisms from U to X. Well, they both correspond to terminal objects of comma category U downwards arrow X. And we know about terminal objects. We know that if we have a couple, then there's going to be a unique isomorphism between them. So we can denote that with an I being the arrow from D1 star to D2 star, and then I minus 1 is the inverse. And there's this unique isomorphism like this, but it's unique having this form here, that it makes this sort of diagram commute. And we get this just by thinking about the comma category and this sort of way of thinking about terminal morphisms as terminal objects of that comma category. And so, since it has these isomorphisms have to commute with sort of triangles like this, we have to have that E2 star after UI is E1 star, and E1 star after UI to the minus 1 is E2 star. So these are our general results, sort of higher level analogues of theorems 2.1 and 2.2. But let's just go down a bit of a level of abstraction now and see what this stuff means for limits. So when we're working with limits, we're going to have D equals C, and E equals this functor category, C to the power of I. We're going to have that our sort of functor u that we're finding terminal morphisms from is this diagonal functor delta blank. Our object, which we're making terminal morphisms to, which we used to call x, is just this functor f. And the actual terminal morphism involves this object d star, which we're calling L, and also this arrow pi. So we have that pi goes from delta L to F. So our terminal morphism then in the category of sets is an object L of C with an arrow pi from delta L to F. Okay, so that's what a limit of F is. Now, to interpret what this remark 1 means, let's suppose we have this isomorphism I from L to L star. Well, then the claim is that L star, together with this sort of vertical composition of natural transformations, we could say pi after delta of I minus 1 is going to be a limit of F. Okay, so that just follows by looking at this in a special case where we're talking about limits. And similarly, 2 means that if we have two limits, L1 comma pi 1 and L2 comma pi 2, and they're both limits of F, then there's going to exist a unique isomorphism I from L1 to I2, which is going to be such that pi 2 after delta I equals pi 1, and pi 1 after delta I to the power of minus 1 equals pi 2. So that's basically the sort of high level run through. Now, just to say, so we can dualize all this stuff, an initial morphism from X to U is an initial morphism of this comma category, X downwards arrow U. Here, we imagine that sort of X is like this kind of disfunctor from this single object category, which is coming in from the left, and U is our general functor. Anyway, a co-limit then of this functor F from I to C is an initial morphism from F to this delta functor, this diagonal functor. So that's all the sort of high level stuff. And then these ideas of initial morphism and co-limit are just dual to the ideas of terminal morphism and limit that I've already discussed. But hopefully now we have a high level view of like where those results about the product come from and the generalizations. If this is a bit too abstract, don't worry. We're going to move on with the more basic stuff in McCarthy's chapter 2 shortly.